Unlocking the curvature of the universe. A journey through hyperbolic grids. Imagine stepping away from a world of rigid, square grids and entering a space where the very lines of the map dance in elegant curves and radiating rays. This is the realm of hyperbolic coordinates, a mathematical framework that swaps the familiar horizontal and vertical axes for two new sets of guides. Curving hyperbolas and straight rays emerging from a central point. The core concept. Mapping a new reality. In a standard coordinate system, we locate a point by measuring how far left or right and up or down it sits. However, in this hyperbolic system, we identify locations using two different metrics. One coordinate determines which straight ray a point lies on as it stretches out from the origin, while the other coordinate places the point on a specific hyperbolic curve that arches through the space. Interestingly, unlike the perfect 90-degree intersections of a traditional city grid, these lines cross at shifting angles. This non-orthogonal nature might seem messy, but it is actually the secret to its power. It allows the coordinate system to perfectly align with the natural bend of physical laws, from the speed of light to the flow of air. Example 1. The cosmic speed limit, special relativity. The most profound use of this system is found in Einstein's special relativity. When objects move at near-light speeds, space and time do not behave like a flat, square floor. Instead, they rotate along these hyperbolic paths. In this narrative, the coordinate representing the straight rays is known as rapidity. While traditional velocity is tricky to calculate when adding high speeds together, rapidity adds up simply and linearly. The hyperbolic curves represent invariant intervals, distances in spacetime that remain exactly the same for every observer, regardless of how fast they are moving. The boundaries that these curves never cross represent the light cones, the ultimate speed limits of our universe. Example 2. Finding your way, LORAN and GPS. Long before modern satellites, sailors and pilots used this exact geometry to navigate the globe through systems like LORAN. Imagine two radio stations sending out synchronized pulses. By measuring the slight time difference in when those pulses arrive, a navigator knows they aren't just anywhere. They are somewhere along a specific hyperbolic line of position. By listening to a second pair of stations, the navigator generates a second hyperbolic curve. The precise point where these two curves intersect reveals their exact location on the map. This time difference of arrival logic remains the invisible backbone of the GPS technology we use in our phones every day. Example 3. The science of listening, acoustic localization. This math also works in reverse to protect lives. In sniper detection systems, multiple microphones are scattered across an area. When a shot is fired, each microphone hears the sound at a slightly different time. Computers immediately draw hyperbolic curves based on these tiny timing differences. Just as with navigation, the point where these curves meet pinpoints the exact origin of the sound, allowing for near-instant detection of a threat's location. Similar hyperbolic signatures are used by ground-penetrating radar to see buried pipes or artifacts beneath the Earth's surface. Example 4. Nature's perfect flow, fluids and heat. Finally, engineers use hyperbolic coordinates to simplify the complex movement of liquids and gases. When air is forced through a narrowing nozzle or flows around a sharp corner, it naturally follows hyperbolic paths. By switching their calculations to this coordinate system, engineers can straighten out the math. What looks like a complex, curving boundary in the real world becomes a simple, straight line in the hyperbolic map, making it much easier to predict how heat will move through a cooling tower or how fuel will flow through an engine. Conclusion. Hyperbolic coordinates prove that the straightest path to a solution isn't always a straight line. Whether it's tracking the stars, navigating the seas, or understanding the wind, this system provides the natural language for a universe defined by invariance and differences rather than simple distances.